Okay, I am going to begin this lecture just essentially, well, by carrying out an example on the expansion of the transfer matrix. Unfortunately, I have no practical way right now to post the screen of the laptop. So what I'm doing is I've got the laptop open right here on the side, and I can look at results, and I will just put the essence of the results here on the board to discuss it. Now, the program that I'm using, the specific file that I'm looking at, is an example that I have already posted in Blackboard. So you can go in there and look at the details if you so need to do that. This is mainly to ensure clarity. So here we have an example on expansion of the transfer matrix. As we said in class, the theoretical issue is that we can calculate the transfer matrix at all the coordinates which are in at the union of the experimental coordinates if we have at least one collocation. That is one point where we have the input and the output. If we don't have any collocation at all, then of course all we get from the identification is C, A, and B, and therefore we get of the transfer matrix the columns where there are, the rows where there are sensors and the columns where there are inputs. Okay? So I'm going to take a look at a system whose, actually let me use scalars. So its masses are 1, 2, 1, 2. The stiffnesses are 1, 1, 1, 1 times 500. The damping coefficients are 10% of the mass, and the structure looks like this: 1, 2, 3, 4. So 1, 2, 3, 4. And we have a applied load at coordinate number 1. So here is an input, and we have an input at coordinate number 4. So we have another input here. We also have, in addition to that, 2 output sensors, one located at coordinate 1. So I'll try to put the output in green. So we have an output sensor here, and we have an output sensor here. Okay? In this case, I am going to solve the problem using displacements for those outputs, so that the transfer matrix that we have is from forces to displacements. Now, the union of the experimental coordinates, the coordinates of this system, let's say, are 1, 2, 3, 4. So the union of the experimental coordinates means that we should be able to get the transfer matrix after expansion at coordinates 1, 3, 4. We don't have either an input and an output 2, and therefore that coordinate is not accessible from an identification perspective. Okay? Let's see. So we are assuming that we perform the ID, and if we perform the identification, we have A, B, and C. In continuous time, we actually got them in discrete time. Be more precise, from the identification, we obtain A1 or A discrete, B discrete, C discrete. Then we perform a discrete to continuous transfer, and at this point we have A continuous, B continuous, and C continuous. If we were to calculate the transfer matrix G, for whatever reason, using our matrices as they came out, we would say the transfer matrix G that we can get is our CC, the identity times S minus AC to the minus 1 times BC. And in this particular case, that matrix would prove to be a matrix that if this system had 4 coordinates, right? 1, 2, 3, 4, 1, 2, 3, 4. What we have of it directly from the ID are the rows where we have outputs, which are rows 1 and row 3. And the columns where we have, well, I should say, we have no more than those rows, and the columns where we have inputs, which are 1, no, is that right? 1 and 4. So we have here 1 and 4. So that means that the actual numbers that we have are really this, 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 and this, right? So we have of the complete matrix, which has 16 entries from the basis of a model, if we knew the model, right? We would have 16 entries for the transfer matrix. It's a 4x4 self-referencing matrix. But we would have, in this case, 4 numbers, that is the 2 inputs and the 2 output rows. Now, when we complete our calculations, we said we would be, because the union of the experimental coordinates is 1, 3, and 4, then we should be able to add this 3, right? Because this 3 is an input. I'm sorry. What did I do here? Columns are the inputs. So the columns are the inputs. Let's damage that. We don't have any extra inputs. We have, well, actually, it doesn't matter. I'm just saying the unit of the experimental coordinates is 1, 3, and 4. So I guess I could put 3 here, which was missing, and I could put 4 here, right, which is missing. And so basically, once I have 1, 3, and 4, we could add this point here and this point here, right? And so now we have, well, of course, and this point here, and this point here, and this point here. So now we have of the matrix the union of the experimental coordinates, which is everything that is at 1, 3, and 4. The only thing that we cannot have is, of course, anything that is associated with 2. So we don't have this number, or this number, or this number, or this number, or this number, right? Or this number, or this number. So the x's are unavailable because the x's are points that there isn't an input or an output. But all the other points are available, even though only the greens are readily available from the output of the thing. The other ones we are able to compute by taking advantage of the fact that the matrices M, C, and K are symmetric. Okay? So continuing, in this particular instance, let's see, how could I best explain, or not explain, I've already explained it in class. How can I best illustrate it? Let's see. Okay, so I think I'll do this. Since you guys have access to this, I'm going to erase here. I think the image is relatively clear on our heads. So I'll erase, and then we'll say, okay, I'm actually just going to show the code in this part. And so I already have my ABCs in continuous time. And so this is the code, MATLAB, as it stands here. I am saying AA and BB is equal to the eigenvalues of AC. What am I doing? I'm taking it to Jordan form, right? And I'm saying L is equal to the diagonal of BB. That is simply because I don't want to deal with this thing being a matrix. I don't need to. Well, I mean, I could. I'm just putting it all in a diagonal because BB is just the eigenvalues, right? Okay. So I'm just checking to see if it looks fine. It's a little bit at the edge, but I guess it's fine. Maybe I should write a little bit bigger. So L is diagonal. Yeah, let me write a little bit lower and a little bit bigger. So I am here, and I am saying A and B is equal to the eigenvalue solution of the matrix AC. And I am saying that L is equal to the diagonal of BB. Then I'm saying tau is equal to the inverse of AA times B continuous, right? And I am saying that phi, which is the equivalent of the C, right, is equal to C continuous times AA. All right? So those are now my matrices in Jordan canonical form, right? Next, I do the essence of the computation, which is compute the constants. Let me see how that's looking. Okay, compute the constants. So I'm going to have for j equals 1 through 8. Now you might do this with only using 4 if you'd like, because this thing comes in complex conjugates, right? So this program is not intended to be most efficient or anything like that, okay? Perhaps most lazy, just putting everything. So for j equals 1 to 8, this is my commentary here. I'm going to calculate the residue, right? So the residue is, by definition, the residue is equal to phi, all the columns, all the rows of column J, the first one, first time around, multiplied by tau, right? The jth row, all the columns. So that's the residue by definition of mode J, right? Now, the entry of the residue that is collocated this is a commentary, right? Is the 1, 1, right? Because it is in the coordinate 1 that we have input-output, right? It's the first input and the first output that are in the same place. Now, that means then that what we have, if you look at the notes, would be that alpha j, that is the constant, will be simply the residue, the 1, 1 position of the residue, right? Divided by the phi, the first entry, because that's where it is, and mode j squared. And then end. So this computation right there extracts the normalization constants, residue 1, 1, jj. Now, I have actually written this program a little bit more refined, more sophisticated. For example, if you were writing a MATLAB code in general, you could put in the input of the file, obviously, which one is the collocated coordinate, right? So this thing doesn't have to be input every time, but just to input it in the top of the form when you call the function. As I mentioned also in class, it may be you don't have to select. If there is more than one collocation, there could be more than one input that has an output at the same location. Then in that case, in this loop, you could choose the most convenient collocation every time. That is, you can calculate this alpha using the collocation that has the largest Φij squared, right? Because under error, that would hopefully be less vulnerable to a large error from round off and things and noise and so on, right? So all those refinements, one can put in when writing a code for having it for good, but this illustrates the concept, right? So at this point we have all the constants alpha. Now, given the constants alpha that have been computed, we now can calculate. Let's assume that the alphas are known. So now that the alphas are known, we can calculate the normalized, remember the building again, 4, 3, 2, 1, right? We had an input and an output here. Sorry. We had an input here and an input here. And I believe we had an output here and an output here, right? Okay, so we do not have the mode shape here, but we can now get it because we can say that now depending which notation you want to use, but mode shape at 4, this is not what I would do, but the mode shape, for clarity, the mode shape at coordinate 4 here, which is not known because we only have it at 1 and 3 in the phi, right, would be simply obtained by recognizing that it is equal to tau the second entry, right, because that's the one that corresponds to the second input, which is at 4, divided by the alpha. Now this in MATLAB notation is 1 by 1, right? So this would be, let me be more precise, MATLAB, this would be dot divided by the constants. So this would be the value of the mode shape in every mode at this location. Divide by alpha, tau, tau, whatever, comma 2 is 4 numbers, and this alpha, or not 4 numbers, 8 numbers, because it's order 8, and these are 8 constants, and you divide this by this and you get 8 numbers, and these 8 numbers are the values of the mode shape here for the 8 mode shapes, right? Now, once we have those, and I call those mode shapes at 4, if you'd like, then again, this is a matter of clarity. Then you could say, for example, the expanded mode shape is equal, in this case, to the phi, right? And the phi is the mode shape at 1 and at 3, and then mode shape at 1 and at 3, and then underneath it we would have the mode shape at 4, close it. So this would be a matrix that would have 8 columns and 1, 2, 3 rows, right? That's the expanded mode shape matrix. We are not adding modes, we are just adding measurements on the modes, right? Because we have added to the mode the 4th entry, which comes from the fact that we had an input there. And the reason how we get it is because we know that the relationship is that the left side eigenvectors must be, right, a constant times the right side eigenvectors. And therefore, if we know this, we know this. If we know this, we know this, right? Once we know the constant. So that's it. So we get our expanded eigenvector. And now once the expanded eigenvector is available and the constants are available, then we can simply obtain, I'm going to use expanded mode-shaped notation. Well, then we can simply say at this point that, let's compute the transfer matrix at any S value that you want. So I am going to select some S, and the one that is actually hard-coded in the thing, pulled out of the blue, could be anything, was -1 plus 8i, right? And so I am saying here for j equals 1 to 8, which is the order, right? This has nothing to do with that 8, but the order. So then the pole residue form, remember, the pole residue form of the transfer matrix is summation of the eigenvector times what? This is tau here, but once we know it's the eigenvector again times the constant divided by S minus lambda, right? So that's the pole residue form of the transfer matrix, in which we've replaced this, the tau by phi times the constant, and where we've already expanded the phi in case there were inputs that helped us do that. And basically, in this case, we just do that simple loop, and so we can say, for example, R is equal to expanded, or oops, I forgot how I called it. Let's say expanded mode shape, right? Expanded mode shape, all the rows, column J, times expanded mode shapes, all the rows, column J, transpose, right? Which in MATLAB is dot transpose, and then times the constant alpha j, right? And then divide it by S minus lambda j, which I think we had it called L, so it'd be something like that, right? So you calculate that R, and then